So for reactions of alkene, you can get major product and minor product. Your major product is coming from most stable carbocation. So when you get the most stable carbocation, it's going to be tertiary first, secondary, then primary. If you have allylic, we had one slide before in the last chapter that showed benzylic and allylic. If it's tertiary, they are a lot more stable than tertiary regular, and then would be tertiary. Then you have your secondary allylic and benzylic, then secondary. So tertiary is more stable than secondary, more stable than primary, more stable than methyl free radical. Because for primary, you only have one electron donor group that is going to help. For secondary, you have two electron donor group, as we talked about last class. These are electron donors. And then for tertiary, you get three groups that they are electron donor, and they are supporting carbocation with electron deficiency. So the greater number of substitutions is going to give higher stability to carbocation. So CH bond is going to decrease, and then the CC bond increases. That's what is happening. Again, the groups that you have around carbocation, they are stabilizing the carbocation by hyperconjugation. Means just these are electron donors. So it's saying the same thing again. It's the now if you have ethyl carbocation versus propyl carbocation, which one is going to be more stable? Propyl is going to be more stable. They are not the same actually. They are not the same. For groups that are alkyl groups, the larger the alkyl groups are, better electron donor they are. So they are generous, at the same time they have more ability to give electrons. So the greater the group is going to be the greater ability to donate electron via hyperconjugation. So it's going to be it's going to give electrons better. So this is a better electron donor compared to more stable than this when you are comparing this two. But if you have a secondary is going to be more stable than the primary, than both of them actually. So if we have A, B, C, and D, is going to be A more stable than B, more stable than D, more stable than C. So the greater the size, larger the size of alkyl group. If you have secondary versus primary, the choice is clear. Secondary is more stable than primary. But if you have two primaries, one with ethyl group attached, one with methyl group attached, the one with the ethyl group attached is going to be more stable. So we have propyl cation more stable than methyl cation. More hydrogen, better electron distribution. When we look for number of hydrogen, if you're looking at the number of hydrogen on the with more carbon, better, like more carbon on the alkyl chain is going to be more electron donor, better electron donor, more stabilizing power. So ethyl attached to carbocation is better than methyl attached to carbocation. Yes, perfect. Very good. Okay, so as long as we understand, because we are dealing with a stability of intermediate this chapter. Stability of intermediate. The more stable intermediate, the major product, because often we get two products and we need to decide which one is the major product, which one is the minor product. We need to know which one is coming from more stable intermediate, and know it by heart that the more stable the intermediate is, the faster the reaction and yields major product. So in order to analyze the intermediate, you need to know which intermediate is more stable. That's why it's emphasizing on separate slide here. If you have like a tertiary or you have a secondary, you have groups with the carbocation that they are the same order, but they have different alkyl size attached to the carbocation, then you want to know which one is going to be more stable. So if you know which one is more stable and you write the carbocation or possible carbocations for your intermediate after the electrophilic attack. So first is electrophilic attack, formation of carbocation. Next step is nucleophilic attack or formation of the product. So when carbocation forms, first we want to know which one is more stable. That's the first thing we want to look at. Second, we have to look for possibility of rearrangement. If there is a methyl attached to it, that was a concern also. If you have a methyl group attached to it, a methyl group attached is going to have the ability for methyl shift. Hydride group attached is going to give you possibility for the hydride shift. And if there is a chance for methyl shift or hydride shift, that's possibility for rearrangement. And the rearrangement happens whenever your degree of carbocation is going to change. If it's going from primary to secondary, or if it's going from secondary to tertiary, carbocation is going to rearrange. If it's going from one primary to another primary, there is no benefit, it's not going to happen. If it's going from a secondary to another secondary, is not worth it. So there would be no rearrangement. If there is no methyl group on adjacent carbon, so we had this example before. So if here is your carbocation, and then you have a ethyl group here, there is no chance for rearrangement. But instead of the ethyl, if you have a methyl group here, if you have a methyl group, of course this is going to rearrange. The plus charge would go to this carbon, and then the methyl group is going to come to this carbon, and you are getting a altered product. You see the structural formula is changing from your reactant to product. So when there is a chance for rearrangement, the rearrangement will take place to benefit the stability, to help your intermediate to be more stable. You're going from primary to a tertiary carbocation, and definitely this rearrangement is going to take place even though you have to move a methyl group. But if the groups are larger than methyl group and there is no hydrogen available on adjacent carbon, then rearrangement will not take place. So you have to know the baby steps first. What is intermediate? It can be carbocation, it can be carbanion, it can be free radical. Second, you need to know if there is a carbocation, would it be, which one is going to be more stable? Third, you need to know if there is carbocation, there is a chance for rearrangement. You look for possible products of the rearrangement. So if there is a rearrangement, you get more than one product, because you get the product before rearrangement, you get product after rearrangement. But after rearrangement, since it's more stable, this is going to give you major product, and this could give you the minor product. So you could get more than two products. Okay, when the electrophilic attack takes place, So when we are adding HCl, just like HBr that I had it on yesterday as an example, Cl is negatively charged and H is a positively charged. In addition reaction, electrophile comes in first, and then nucleophile comes in second. So when the electrophile comes in, is going to attach to one of these carbons, carbon 1 or carbon 2. The carbon that takes the hydrogen is going to make the other carbon to take the positive charge. Also, these are like simple and again like a baby sentences. So it's not, the very simple way of talking about these reactions. The H plus, whichever of these two carbon takes the H plus, the other one would be positively charged. So you have a CH2 here. We talked about Markovnikov addition. Hydrogen is going to get to be added to CH2. The other carbon would take the plus charge. If that is the norm, then that is the trend, or that is giving you the intermediate, is the product. The product also is called the Markovnikov product. So if this doesn't happen, like if the hydrogen goes to carbon 2, your carbon 1 is going to take the plus charge, and that is a primary, so it's not going to happen. So this is very slow, very minor product from this, and this would be your major product. So primary carbocations, because they are not stable, is not going to form. The Markovnikov, I keep saying it, and then in few slides, I'm going to show you exactly. Markovnikov is the person, a scientist, who presented the first time the idea of what is going to be the major product, what is going to be the minor product. So basically is a rule, like octet rule, like Markovnikov product. Markovnikov product is saying that when you bring HX to add to CC double bond, H will add to the carbon with greater number of hydrogen, and X will add to the carbon that has least number of hydrogen. And rich gets richer. That means the carbon with greater number of hydrogen will gain more hydrogen. The other carbon would get the counterpart if you have the HX being added to the carbon-carbon double bond. So this is the Markovnikov product. Okay, if you change the condition of the reaction, if you bring a catalyst, you change the condition of the reaction, and you force this reaction to form 1-chloro, then the product is going to be anti-Markovnikov. That means that it did not follow the Markovnikov rule. If this forms, this is a anti-Markovnikov. This is the anti-Markovnikov. Okay, so that's anti-Markovnikov product, and you have to force the reaction go through anti-Markovnikov, because you have to change the intermediate. You have to change the intermediate and make sure that the intermediate still is stable, because the more stable intermediate is going to give you a major product. Okay, if you add HI to this product, to this reactant, I'm sorry, which one is going to be, what are the steps? Because the answer to which one is already there. What are the steps? You have the HI. Which one comes in first? Okay, H will come in first. And would H connect to 1, attack the carbon 1 or carbon 2? Carbon 2, because carbon 2, so count the number of hydrogens. Carbon 2 has 2 hydrogen, carbon 1 has 1 hydrogen. When you bring H, H is going to attack carbon 2, and as a result, is going, the carbon 1 will take the positive charge, and when carbon 1 takes the positive charge, you will get a tertiary carbocation. If carbon 2 takes the positive charge, you will get secondary carbocation. Which one is more stable is the tertiary. So before you add the hydrogen, you have to look at the structure molecule for your reactant and say, okay, if this one is carbon 1 takes the H plus, carbon 2 would change to carbocation, and carbon 2 is a secondary carbocation. If carbon 2 takes the H plus, then carbon 1 is going to take the plus charge, change to carbocation, and your carbocation is going to be tertiary. Which one is going to be more stable is the one that would cause tertiary carbocation form, and that would yield to major product. So we have a major product there. Okay, so if this is like an uneven distribution of alkyl group around carbon-carbon double bond, or carbon-carbon double bond that are not symmetrical. If they are symmetrical, that means if you had another CH3 group here, it didn't matter which one would take hydrogen, which one would take the I. But if you have different number of alkyl groups attached to carbon-carbon double bond, then the one that yields to more stable intermediate would yield the major product is going to happen more likely. For cyclohexene, we have cyclohexene, again, is the same. This is just repeating too often, so it kind of sinks. It's easy for you to just look at this structure without thinking, say, okay, hydrogen is going to be added to this carbon, bromine would add to the other carbon. And then if they ask for mechanism for this reaction, then you have to say, okay, this is the HX being added to alkene functional group, CC double bond. H plus is coming in first, then is going to be the Br minus. This is my electrophile that is being added. That's my nucleophile is being added. Okay. Second, when the electrophile comes in, the intermediate that is forming is going to be carbocation. Now, if H is added to carbon 2 versus if it's added to carbon 1. If H is added to carbon 1, carbon 2 would take the plus charge and changes to carbocation. That is going to be a secondary carbocation. So if it's a secondary carbocation, is less stable than if the other case would happen. If H is added to carbon 2 and plus charge would be on this carbon. If the plus charge in that carbon is going to be, let me just draw this. Let me see if I can, it might take some time, but it's okay. So you have a CH3 here to go back and forth, I mean. You want to add HBr. So we already know that this is our HX, addition of HX. Electrophile is going to add first. So we have a H plus and a Br minus is going to happen in 2 steps. So first is going to be, this is like what we are thinking before we even write the mechanism for this reaction. Electrophile is going to come in first. So that's the first step. And the second step, nucleophile would come in. And your nucleophile is this, Br minus, electrophile is a H plus. So what is happening in the first step, H plus is going to come in, and H plus has a choice to go to carbon 1 or to go to carbon 2. Going to number this 1 possible and then 2 possible. So if 1 happens or if 2 happens, what would be the intermediate? Because that's the first step. If 1 happens, that means H is added to this carbon. You are going to draw the backbone of the molecule. You have your CH3. If this carbon with the route 1 takes the hydrogen, So I'm going to put the hydrogen here. What happens to the other carbon? The other carbon takes the plus charge. Remember, one carbon takes the hydrogen, the other carbon takes the plus charge in the first step of this addition reaction of alkene. When you have a HX, H plus comes in first, carbocation forms. Which carbon takes the plus charge is the carbon that did not take the hydrogen. If route 2 is going to take place, so we are going to write the backbone of the molecule. Now hydrogen is added to carbon 2, so we have a hydrogen here, and the other carbon is going to take the plus charge. These are two possible routes. So if one takes place, we are going to end up with tertiary carbocation. If 2 happens, we are going to end up with secondary carbocation. And because tertiary is more stable than secondary, this is going to be major, and this one is going to be minor. Now, on the next step, your nucleophile comes in. So this is the second step. In the second step, when the nucleophile comes in, your product is going to be CH3, Br, and H is added here. You don't have to write the H. For this minor product, for the second step, nucleophile would attach to the carbon, so with the plus charge, and hydrogen would attach, stays in the other carbon. So this would be your minor product. Major product is coming from more stable, intermediate, and minor product is coming from less stable, intermediate. Is that clear? Okay, perfect. Okay, let me go to sharing file again. That's why I said it might take, because I don't have enough space there, but it's okay. Gonna So H adds to the carbon with the greater number of hydrogen for major product, and Br or nucleophile would add to the one with least number of hydrogen. So let's look at this one. What would be the major product? Why this product is major product? If hydrogen is added, hydrogen, if it's coming to carbon 1, carbon 1 has 2 hydrogens, carbon 2 has 1 hydrogen. So carbon 1 with 2 hydrogen is going to gain the hydrogen, and carbon 2 has 1 hydrogen, less number of hydrogen will gain the counterpart. And this is going to be your major product. This product is known as the Markovnikov's product, or the rule is Markovnikov rules. So in the Markovnikov, based on the Markovnikov rule, for all alkene, for electrophilic addition reaction, that means electrophile comes in first. That's electrophilic addition reaction. That's all it means, that electrophile comes in first. When electrophile comes in and adds up to sp2 hybrid carbon, that means carbon-carbon double bond. Because when you bring the electrophile, H plus is not going to come and attack this carbon that is sp3. It's going to go to one of these 2 carbon. The carbon bonded to greater number of hydrogen will gain the H plus, and the other carbon will gain the nucleophile. And that is the Markovnikov rule. Okay, based on the Markovnikov addition, what would be the major product? You're adding HBr to this structure now. So we are going to count the number of hydrogen at this point. Hydrogen should add to carbon number 2 or 3. Hydrogen 2, carbon 2 has how many hydrogens? Carbon 2 has 0 hydrogens, right? And carbon 3 has 1 hydrogen. Just counting number of hydrogens. Because carbon 3, the reason I put 3 because if I start numbering 1, 2, 3, and 4 like this, okay? Carbon 3 has 1 hydrogen, carbon 2 has 0 hydrogen. What is Markovnikov rule? Markovnikov rule, it says that hydrogen is going to add to the carbon with greater number of hydrogens. And what is the reason for that? The reason for that is, or justification for that is, when the hydrogen is added to the carbon with greater number of carbon, then the plus charge would add to the carbon that has less number of hydrogen, or is more substituted, or has a higher degree. It's probably a tertiary or secondary, okay, because it's attached to more number of carbon, not hydrogen. The carbon with least number of hydrogen would take the Cl, or the counterpart, the nucleophile. The carbon with the greater number of hydrogen would take the hydrogen, and that is the Markovnikov rule. So the Markovnikov rule, again, the hydrogen is going to add to the carbon with greater number of hydrogen, and then the extended rule, it says hydrogen is going to add to a carbon from carbon-carbon double bond, because those are the only carbon in question. It will add to the carbon that gives you the most stable intermediate. That will give you more stable intermediate, because if the intermediate is not carbocation, is carboanion, or if it's free radical, same thing is going to happen. It's going to be following the same trend, but it will happen with the extended. So it's not always carbocation, it could be also free radical. So again, we are going to get intermediate that is more stable. Okay, so you have a secondary intermediate here, you have a tertiary intermediate. That's why this is going to be your major product. Okay, if we number these carbons up here with the example, it's going to be carbon 1, 2, 3, 4, 5. And if I add HBr, H will add, for this example that I wrote, hydrogen will add to which carbon? Okay. So carbon 3 has 1 hydrogen, carbon 2 has no hydrogen. So H should add to the carbon with greater number of hydrogen. It's comparing of 0 to 1. 1 is greater, so H will add to this carbon 3, and plus charge would add to the carbon that has less number of hydrogen. But when hydrogen add to carbon number 3, the other carbon will be positive, which is the most stable intermediate. And similarly, for this reaction, we have 2 hydrogen on this carbon, and one hydrogen and carbon on the left side. Hydrogen is going to add to CH2, and Br will add to the other carbon. Because when you add the hydrogen to CH2, you are going to get a secondary carbocation. But if you add the hydrogen to the carbon on the left, you would get primary carbocation, which is going to be less stable. And because it's less stable, it's not going to form, or if it forms, it will give you minor product. I had this one on the new slide, like blank slide. Do you have any question about this reaction? Methyl cyclohexene. I already had it. I wrote the mechanism for you already. Do you have any question about this? Again, if the line angle structure is given to you, it's not going to give you the number of hydrogens all the time. You have to add the hydrogens before you start answering questions. So if it tells you this molecule here, CH3, without drawing the hydrogen there, you still have to count that hydrogen because it's understood that there is a hydrogen in this carbon. Otherwise, this carbon is going to have only 3 bonds. So you have to add the hydrogen, and that's the healthiest and the best way. If the line angle, you're talking about addition of hydrogen to carbon with the most number of hydrogen. The best way for you to change your line angle structure to condensate structure, or make sure to assign the hydrogen, draw the hydrogens for each of the carbon, and then the number of hydrogen. So this carbon does not take any hydrogen here. This carbon has 0 hydrogens because already has 4 bonds to carbon. So this one has 0 hydrogens. Okay, no hydrogens. I put parentheses in H in parentheses so you don't read that OH, even though there's voice, but still I don't want to confuse you. So there's 1 hydrogen for this carbon, 1H, 0H, 1H. So hydrogen is going to add to the carbon with greater number of hydrogen, and Br will add to the other carbon, and that's why you get your major product. Okay. So when you have a chemical reaction, I said you have reactant, reagent, product. Sometimes you need catalyst, other times you don't need catalyst. Any of those could be questioned. You could have the product, one of the reagent, and then what is the reactant? You could have reactant and the product, what is the reagent? Or you could have reactant, reagent, what is the product? So this question gives you the product and it's asking what should be the reactant that produces this product. What reactant can you use? In this case, we know that when HBr is added, is going to be added as a H and Br. Br adds to carbon number 3. So 1, 2, 3, 4, 5, 6. So Br is added to carbon number 3. Where is hydrogen added? Hydrogen, in this case, it could be added to carbon 2, or it could be added to carbon 4. So originally, the carbon-carbon double bond would be either on the left side of this carbon Br or on the right side of the carbon with the Br. And either one of these can give you the same product. Okay. So they are the same. Okay. Since these two are the same, they both give you secondary carbocation. So you have 2 products, that 2 reactants that could give you the same product. Which one is the major product? Which one is minor product? Which one is major? Which one minor? They're all major? Okay. For the first reaction, for this first reaction, you could get 2 products. If you start with the 3-hexene, if you start with 3-hexene, you get only 1 product. It's the same product. So you could get the plus charge on carbon 3 from this end or carbon 3 from the other end, and either one of them would give you 3-bromohexane. So when you go back to the choices, since either one of these can give you the same product, and both of them would give you secondary, this is a better choice for the answer. So both of them are correct, but a better choice would be this one. Because if you use the compound as the reactant, you could get 2-bromo or you could get 3-bromo. Half of your product is going to be the desired product that you needed, but if you choose 3-hexene, you only get 1 product, and that is the 3-bromo. Either it doesn't matter which one takes the bromo, is going to be 3, because you count from left to right or right to left, still is going to be 3-bromo. The only way you can catch these is if you do end of the chapter problems, you would do the OR assignments, you do co-op assignments, and I suggest you do all of them before you take your exam. This one is for exam 3, is not even for exam 2, but even for exam 2, you have to do end of the chapter problems. You have to finish the OR assignments for all 3 chapters that they are on exam 2 before you start your exam. It's not if it's proctored or it's not proctored. It's the fact that how much practice you had for these chapters, because these are new type of reactions. There's a lot of detailed and like specific products that you could get and a specific condition. And each one of them is presented. They cannot all be presented by PowerPoint, but they are all presented and studied using the OR assignments. So make sure you submit those before you take your quiz. And same thing for the exam. Okay, so we get the better choice would be 3-hexene versus the 2-hexene, even though both of them give the same product, with exception that if you choose 2-hexene, you get half of the product as the desired, what you needed. But if you use 3-hexene, 100% of the product is going to be 3-bromo. Okay, questions? Any questions before we move to different intermediate? No questions? Okay. If we change the mechanism of the reaction, instead of instead of our reaction going through formation of carbocation as intermediate. If the intermediate is free radical, which we are changing it in order to get anti-Markovnikov product, how would the mechanism be, and which one is getting, which one would yield to major product and more stable intermediate? So if we add peroxide while we are adding HBr, if we are adding HBr, we add peroxide as a catalyst. How would the presence of peroxide change the product? So if you're adding peroxide as catalyst, peroxide is going to react first. So peroxide is like H2O2, is hydrogen peroxide. The bond for H2O2, it looks like this is the peroxide ion with 2 negative charge. When it's attached to 2 hydrogen, it's called hydrogen peroxide. And I'm sure you all know that hydrogen peroxide is very unstable. And sometimes they say, do not use any like toothpaste that it causes or produces peroxide or contains peroxide, or it produces like the free radical. The reason they say don't use it, because when it does react, or when you are using it, it can break and it can give you these 2 species, which is the 2 free radicals. And free radicals are not safe. Free radicals are very reactive, and sometimes they say it's carcinogen, and try not to use it. Free radical in body also is not safe. It's going to cause like aging. That's why they say vitamin E, vitamin C, they are going to act as an inhibitor, and they react with the free radical, and they stop the reaction of the free radical chain reactions. So when you say peroxide, you're not talking about hydrogen peroxide, you're talking about alkyl peroxide. So instead of the hydrogen, you have here like a CH3 and CH3. So it doesn't have to be hydrogen peroxide always. When you say peroxide, is alkyl peroxide or hydrogen peroxide. So if we are using alkyl peroxide, the alkyl peroxide is going to first produce free radical. So alkyl peroxide is going to have hemolytic cleavage in the peroxide ion, and you will get the free radical. This free radical now is going to abstract the hydrogen from HBr. When it takes the hydrogen from HBr, how many electron is needed to come from the, yes, you get 2 free radicals. How many hydrogen you will get, how many electrons do you need from the HBr bond to form bond with the free radical of RO? Do we need electron from hydrogen to form this bond? Yes, and we need 1 electron, right? We need 1 electron, because when you have dash line, that means 2 electrons. This is just bringing, the free radical is bringing 1 electron. The hydrogen must bring 1 electron. So when the free radical is taking away the hydrogen, is going to take 1 electron away, and then bromine is going to end up with 1 electron, and that is your free radical, bromine free radical. So in the first step of the anti-Markovnikov addition, or addition in presence of peroxide, in the first step, Br free radical is going to form. Bromine free radical is going to form. Now, bromine is going to attack the carbon-carbon double bond. If bromine forms bond with carbon 1, 2, 3, and 4, if bromine forms bond with carbon number 3, then carbon 2 will take the free radical. Again, bromine has 1 electron. It takes only 1 electron from pi bond. The other electron is going to go to the other carbon. So basically what you have here is going to be hemolytic cleavage, 1 electron to this side and 1 electron to the other side. So when bromine comes in, forms bond with carbon 3, carbon 2 would take the free radical. If bromine forms bond with carbon number 2, carbon 3 would take the free radical. And which one is more stable? Which one is going to be more stable? When is attached to carbon 3, because carbon 2 would give you tertiary free radical. And because it's a tertiary free radical, is going to be more stable. And then this is going to add, hydrogen will add to that free radical. When you have the product, did it follow the Markovnikov? So if you add the hydrogen here, did this one follow the Markovnikov, this product, Markovnikov product? What is the Markovnikov product? If you want to have a Markovnikov product, that means when we are adding HBr, H should add to carbon with more hydrogen, Br should add to carbon with the less hydrogen. But since H is going to add to carbon with less number of hydrogen, this is known as the anti-Markovnikov product, because Br is added to the carbon with hydrogen and H is added to carbon with no hydrogen and is going to be anti-Markovnikov. So if you alter the mechanism of reaction, instead of carbocation or directly adding HBr, you would add the HBr and the peroxide at the same time. So if you add the ROOR peroxide and this together, you are altering the mechanism of the reaction. Why do you want to do that? The same idea yesterday we said, either when you are studying, your professor says you want to make 1 bromobutane instead of 2 bromo, or you're working and your boss would say you have to make this, or you have your own place and you want to make the 1 bromo instead of the 2 bromo. So the product has not formed yet. I was just saying that when you get the H there, this can attack the HBr basically, and then takes the hydrogen. Now, which one is going to be more stable? Definitely this one is going to be more stable, but that's not following the Markovnikov rule. Br has been added to the carbon with greater number of hydrogen, but it follows the extended Markovnikov rule because it's going to generate more stable intermediate. The product is anti-Markovnikov product. So because this is least stable, is not going to form. So this plus the HBr, you have 1 electron from here, is going to make a hemolytic cleavage here to take the hydrogen. So the product is going to form. Acid-catalyzed reaction. When you add water to alkene, alkene is non-polar, is not going to even dissolve in water, is not going to react with water. So because it doesn't react with water, you don't have a strong acid from the water. It's not like a HBr that you would have the H plus dissociated and attacking this. So because no reaction takes place here, you have to bring a catalyst. So you are going to bring a H plus as a catalyst. When you bring H plus as catalyst, instead of water attacking the first step, is going to be H plus attacking the CC double bond first. Now, which one will take the hydrogen? Carbon 1, 2, or 3? The H plus. Carbon 1, because carbon 1 has 2 hydrogens, carbon 2 has 1 hydrogen. So rich gets richer. If it's Markovnikov addition, then we know that is going to be carbon 1 taking the H plus. Carbon 2 in this case is going to take OH. If you remember from the summary of the reactions, I said when you are adding H2O, you are adding H and you're adding OH. So one carbon is going to take H, the other carbon will take the OH. Okay, so if you bring a catalyst here, when you use the catalyst, then the reaction can take place. And when this reaction is taking place, you have H being added, the net result. So you have to look at this way. This reaction is called hydration of alkene, or adding water to alkene. What is the net result? H is going to add and OH will add. The final product is going to be alcohol. The question is this addition Markovnikov addition or anti-Markovnikov addition? Which you are going to memorize this. This is called direct hydration, adding water. And when you learn indirect hydration, then you would appreciate this. This is like a direct addition of water. That means you're just acid-catalyzed this reaction that will take place. Is a Markovnikov addition. H will add to carbon with more number of hydrogen, and OH will add to carbon with least number of hydrogens. So H plus is going to act as the electrophilic proton. It's going to follow the Markovnikov addition. H plus adds to sp2. The carbocation is going to form, and when the carbocation forms, you have see the carbocation is forming, is the first step or slow step of the reaction. H will add to this carbon. The carbocation is going to form on the second carbon, and you have a secondary carbocation. And the next step, H2O is going to come in. When H2O comes in, let me just put the example on a blank page so you could see better for the mechanism of the reaction. So when we have the H2O coming as a nucleophile, is going to take over the plus charge. Now we have a plus charge on the oxygen, which makes the oxygen very unstable. Then is the story starting again. We have oxygen with plus charge. What should we do? We have two choices. Can you tell me what are the two choices? Because if you repeat it, and if everybody, at least repeat in your mind, even if you don't put it in the chat, if you repeat this, it's going to help you to remember longer. If you have OH2, would you have a plus charge on the oxygen? What is the solution? Like you have this case here. You have oxygen with 2 hydrogen, or OH2, attached to this carbon, but there is a plus charge on oxygen. What should we do? What are the two choices? Remove water. If we remove water, the plus charge goes back to the carbon, then we end up with what we had as intermediate. What is the other choice? What's the second choice? No. We already have done here is the protonated. Is already protonated. You probably meant like we need to deprotonate this, because we need to take the H plus away. We need to take the plus charge away, and our second choice would be to remove H plus. So the two choices when you get to this point, when you have plus charge on water, plus charge on oxygen, you can remove H plus or remove H2O. Different cases would require different step. So in this case, if you remove water, is going to go back to the intermediate, and that's not beneficial. We want to go to product. In order to go from this intermediate to product, we can remove the H plus. You take the one of the hydrogens with the plus charge, and you end up with product. So you have to remove H plus. In this case, the addition is Markovnikov addition. Okay, I'm trying to. Looks like I have to stop this. Okay, let's example of hydration of water. So we have CH3, CH, double bond, CH3. You want to add water to this in presence of H2SO4. Okay. What is going to be the first step? In the first step, why do you bring the H2SO4? Because this reaction is not going to take place without acid catalyzed. So what's going to happen here? H2SO4 plus H2O. This is going to act as an acid-base reaction. It's going to generate H3O plus and HSO4 minus. That's the acid dissociation. So we are going to get the H3O plus here. H3O plus is acting as electrophile. Electrophile is going to attack one of these two choices, carbon 1 or carbon 2. Now, I'm going to have two choices here, 1 or 2. If H plus adds to carbon 1, I gave too many, and this is something that is a disaster. I give too many bonds to this carbon, poor carbon 1. So it has to be CH2. It should have been CH2, sorry. So if H plus is added to carbon 1, what would be the intermediate? The intermediate is going to be CH3 because the other carbon would take the plus charge, right? Plus charge and CH2. If H plus, so if H plus attaches to carbon 2, we are going to get CH3, CH2, and CH2 plus. Which one is major? One or two? Route 1 or 2? 1, because it is giving more, okay, is giving more stable intermediate. So this is going to happen. And this is not going to happen because it's a primary radical. Next, on the next step, water is going to come in as our nucleophile. So this is the first step. After formation of our electrophile, which is H3O plus. And the second step, water is going to come in as the nucleophile. So second step, H2O comes in as nucleophile. H2O is going to come in and form bond with the carbocation. We are going to get CH3, C, oxygen, hydrogen, and hydrogen. This is the H2O. H, CH3. What happened to the plus charge? Would the plus charge be cancelled by bringing H2O or remains? Am I bringing any negative charge here to cancel the plus charge? No. So if I don't cancel the plus charge is going to stay. It was on carbon, but since nucleophile is coming to take care of that plus charge, or is going to rescue or stabilize this carbocation, that plus charge is going to move down toward the oxygen. And this is not stable. Okay, this not stable. Why is not stable? Because you have the plus charge on oxygen. What are the solutions? You have to remove the plus charge. How can you remove plus charge? The two choices is remove H plus or remove water. Which one should I use? These are the two choices. Which one should I use? One, I have to remove H plus. How am I going to remove H plus? H plus can be removed by what you have here, HSO4 minus. HSO4 minus can remove the H plus from here. So if it removes the HSO4 minus, it can come and abstract one hydrogen. It's going to take away the hydrogen, not the two electrons. So these electrons are going to go back to the oxygen. Now we can cancel that plus charge. Okay, so we are going to end up with CH3, CH, OH here, and a CH3. Net result, going from our reactant to product. What's the net result? Hydrogen added to the carbon with the most number of hydrogen, OH added to carbon with the least number of hydrogen. This product is called Markovnikov product. This reaction is called hydration of alkene. The reaction does not go through without the catalyst, so is an acid-catalyzed hydration of alkene. The product is Markovnikov product. So you have to know all these factors and facts about hydration of alkene when you are using acid-catalyzed. The reaction is going to be acid-catalyzed. The reaction is going to produce Markovnikov product. What happens to the catalyst? Catalyst is a species that is not going to be, it's going to be recovered at the end, right? Remember what happens, we have HSO4 here, minus is going to abstract the H plus, and it changes to H2SO4. So it speeds up the reaction, but is not consumed in the chemical reaction. So it's going to help the reaction to happen, but it will be recovered at the end. So I have HSO4 minus taking one hydrogen, it changes to H2SO4. Okay, when we are adding water, then the product is going to be Markovnikov product. H will add to carbon with more number of hydrogen, and OH will add to carbon with the least number of hydrogen. When you are adding H2SO4 as a catalyst, is going to produce the hydronium ion, and your hydronium ion is acting as electrophile. So these are just steps of the reaction. I had it on the other blank slides anyway, so you have that. Now, if you add alcohol to alkene, what's going to happen? What will happen if you add alcohol? When you add alcohol to CC double bond, you're basically, this is the alcohol. You have to kind of, these are like little tricky, very simple points, but it's going to help you to answer multiple choice questions faster if you actually remember. Alcohol is like a ROH, right? Water is like a HOH. When we add water, when you add water, for water you add H. Please write these in your own words somewhere. So when you add water, you add H and you add OH. Okay, you add H and you add OH. H plus and OH minus. What happens if you add alcohol? When you add alcohol to the when you add alcohol to carbon-carbon double bond, you're not adding OH. What you're adding instead, you have to remember this part, you're going to add H and add OR, just like water. You're adding H plus, you're adding OR minus, or you're adding H, you're adding OR. Is not adding OH and adding R, because this is going to make a difference when you are answering multiple choice questions. Okay, you're adding H plus, you're adding OR minus. Addition of alcohol to alkene is also acid catalyzed. So H plus comes in first, just like HBr, adding HBr. The first step is going to the same. So is an acid catalyzed reaction. Carbocation is going to form first. When carbocation forms first, then you are going to get H plus added to carbon with greater number of hydrogen, because the carbocation that is forming is going to be more stable if it follows the Markovnikov rule. Whenever carbocation is forming, you're going to get Markovnikov product. That means hydrogen will add to carbon with greater number of hydrogen, and the other piece, the counterpart, would add to the other carbon. So if the mechanism was not the question, you would say, I'm adding alcohol. This is alcohol. It looks like ROH. I'm not adding OH and R. I'm adding H and I'm adding OR. So H will add to which carbon? 1, 2, or 3. If it adds to 1, 2 would take the plus charge. It's not going to add to 3 because that's impossible. It's not sp2 carbon. If it adds to 2, this one, the primary carbocation, is going to form. So that's not stable. The only choice you have, H is going to add to carbon 1, and OR will add to carbon number 2. And that's how you get your product. So think about, I'm just repeating myself, that when you are adding alcohol, you're adding H to one carbon and you're adding OR to another carbon. And you're not adding from the R side, you're adding from oxygen side. That's why I call it OR, not RO, even though when you write it, it's like ROH. Okay, so you're adding from the oxygen side. What's happening on the slow step? Formation of carbocation. So the more stable carbocation, the faster the reaction is going to be. How the carbocation is forming is the acid catalyzed. So acid is going to protonate the alcohol first, and then you get just like the H3O plus. And even if you just say H plus is going to come in first, not wrong, because some books, like the client that I'm using for another college, is going to, it's just saying H plus comes in and protonates this. But H plus is going to protonate the alkene first. H plus would add to the carbon with greater number of hydrogen. You get your carbocation. And next step, you're getting the alcohol added as a nucleophile. So this is the second step when the nucleophile is coming. In the first step, this is the first step, your electrophile is coming. Okay? Addition of the electrophile. So second step is addition of the nucleophile. So your nucleophile is coming. When the nucleophile comes in, what is the situation again? What do you have here? Plus charge on oxygen. Is that stable? No. What is the solution? The solution, when you have like an alcohol, you have an O, CH3 here, and H with the plus charge. The solution is, the number of choices you have is the same, slightly different from when you had the water. Here, you either remove, you're going to remove H plus, that which yields to the product, or you remove alcohol. So this is the choice, but the second choice, which we are not using today, is CH3OH. We don't choose this choice because if we do that, it's going to go back to forming carbocation. So when I have plus charge on oxygen, it makes the molecule very unstable. One of the choices is to remove the whole molecule. And the second choice is to remove the H plus. If you remove the H plus, when you remove H plus, you're not removing any electron. So you give, there is a plus charge here, you give this electrons, pair of electrons back to the oxygen. That is going to cancel the plus charge and is going to make you have a product. What's the difference between intermediate and the product? When you have intermediate, that means it's not stable. This is an intermediate. That's an intermediate. You cannot isolate that. Like you try anything you learned in the lab, distillation, recrystallization, extraction, nothing is going to work on this. You cannot isolate this. Intermediate, it forms and is consumed. We don't have this as a product. Is this a product? Yes or no? Is this a product? Where I have the question mark. Because this one, everyone knows that that's a carbocation. That's not a product. Is the intermediate. We know is a carbocation. This one is not a product. Why is not a product? Because your product cannot carry a plus charge. This is still intermediate, but is the intermediate in the fastest step. So if you have the energy diagram, you have like first intermediate, you could have second intermediate, and you could have like a third intermediate. Okay, so this is intermediate. This is not stable, and if it's not stable, it cannot be isolated. It can't be classified as product. Your job is not done until you make sure that your final product is a neutral product. So to take care of that plus charge, you remove hydrogen. And what are you using to remove hydrogen? You can use any base. Solvent can be used, alcohol can be used, water can be used, any nucleophile, anything that has negative charge or it has pair of unshared electrons. Like if you're talking about water, water has pairs of unshared electron, so it can remove H+. Yes, so we can use H2O to remove H+. We can use alcohol to remove H+, because alcohol has pair of unshared electron. So this is the solvent. Can I bring water to this reaction to remove the H+ when I have the alcohol? If I bring the water in this reaction, it's going to give me probably a mixture of two products. Water is going to come in presence of H+, it can do hydration here, and then instead of getting ether as the product here, I could get mixture of ether and alcohol. So it's better to keep your reaction mixture clean. How could you keep it clean? Like if you're using, like for chapter 7, when you are using this as a base, don't use water as solvent, use CH3OH solvent. Don't use ethanol as solvent because it's very similar to the nucleophile that you are using. So in this case, we could remove this with water, and you were right, we used before water to remove the H+. But if alcohol also has pairs of unshared, why would I bring water? But what would be the net result? The final thing is that this is not stable, and this is going to lose the hydrogen to HSO4 minus anyway, because our HSO4 minus has to change to H2SO4 to become stable anyway. Okay. What would be the final product here? The final product, if you have H added to this hydrogen, plus charge would form on the carbon 2. A plus charge on carbon 2 is secondary. There is a chance for metal here to give you a tertiary carbocation. So you could have two products here. One product without rearrangement, one product with rearrangement. If it does rearrange, it's going to give you tertiary. If it doesn't rearrange, you have the secondary. So you get two products. When there is carbocation, there is a chance for rearrangement. So anytime you have carbocation, there is a chance for rearrangement. And if the rearrangement is going to benefit the intermediate, rearrangement will take place. So you should always look for the possibility. So if they are asking what's the major product here, the major product is the rearranged product. All products is going to be both of them, this plus the major plus the minor. You get product for rearrangement, you get product after the rearrangement. So you get mixture of two products. So methyl shift is causing the rearrangement here. Question? Okay, the internet is getting a little weak and it keeps disconnecting the video. As long as you see the slides and you have the audio, that's good. Do you have any questions? Any questions? You have to memorize the reactant, the reagent, the product. You need to know the mechanism for the reaction and what type of product, based on the mechanism, what type of product you are going to get. Is it going to be Markovnikov product or is it going to be anti-Markovnikov product? Those are few things that for every reaction you have to consider. Is there a chance for rearrangement for this molecule? Yes. Hydrogen is going to be the Markovnikov rule. Hydrogen is going to be added to this carbon because it has more number of hydrogen. The plus charge is going to form on the second carbon. This is going to be secondary. It's a secondary carbon. A neighboring carbon, there is a methyl group and there is a hydrogen. Which one is easier to move? Hydrogen should move or the methyl should move? Hydrogen is lighter than methyl, so hydrogen is going to bring the pair of electrons. That's why it's called the hydride. So when we say hydride, that means hydrogen is moving with the pair of electrons. As a result, the other carbon will be positive. The carbon that is losing the hydride is going to be positive. So we get a rearranged carbocation and is tertiary and is more stable. And if it's more stable, it would yield major product. So you don't always go, because you learned about Markovnikov and it sounds so cool. So you don't want to go just with the Markovnikov product. You want to draw the structure of your carbocation that is following the Markovnikov and put your special agent hat on, look for possibility of rearrangement. If there is a possibility of rearrangement, then predict the major product, which is going to be major product. It actually does follow the Markovnikov, because if you look at the net result, your carbon 1 has gained the H plus, the hydrogen, and the carbon 3 that is gaining the Br still is the least substituted. Even it has lower number of hydrogen compared to, it's the same number of hydrogen, but it's going to have low number of hydrogens compared to this carbon. So is the Markovnikov, but rearranged Markovnikov. Anti-Markovnikov is different. Anti-Markovnikov is that hydrogen will not add to this, Br will add to this one. Sure. Okay, before we look at the anti-Markovnikov, we are going to look at this reaction that rearrangement does not take place. So it's not always that rearrangement will take place when carbocation forms. What is this degree of the carbocation? After hydrogen adds to the carbon 1, plus charge on carbon number 2, this is a secondary carbocation. So secondary carbocation, if shift takes place, this is also secondary carbocation. Going from secondary to secondary, is it worth it? No, it's not worth it. So it takes a lot of energy to move the hydrogen and is not going to increase the carbocation order. So if it goes from secondary to secondary, it's not going to happen. So it stays as the original secondary. Remember on the schedule, we have extra days that it says finish up the course material. So I'm going to, that's why I'm using that time actually to spend more time on chapter 8. It's chapter 8 important. So I'm going slow, I'm repeating often, but it doesn't mean that you can relax and not study for chapter 8 ahead of time. So make sure you start the OR assignments right away for chapter 8. As soon as you're done with chapter 5, 6, 7, start the OR assignment for chapter 8. Bring your questions. Okay, there are 2 questions and I'm going to use the time to answer those 2 questions. One was like anti-Markovnikov addition with the rearrangement, and the other one is the question that I got via email, and I have to explain how the order of the nucleophilic effect, because we do have the explanation, but this is the example that was on the OR question. So before I move to those 2, do you have any question about this rearrangement not taking place actually in this example? Rearrangement will take place if the order of carbocation is changing, if it's going from primary to secondary or from secondary to tertiary. In this case, when carbocation forms is already secondary, and the rearrangement is going to give you another secondary, there is no benefit, is not gonna happen. So what type of questions you're going to see on the test is like, you get like 4 different compounds and it says which one rearrangement will not take place. So in order to answer a question like that, if you get only this and say, would the rearrangement take place or not, it's easy. But if you get 4 compounds and you get name for 4 compounds and you want to decide which one rearrangement doesn't take place, first of all, if there's name, you have to write at least the condensed formula. Okay, you have to write at least the condensed formula, and when you look at the condensed formula, then you draw the carbocation that is forming. Then you are going to look for rearrangement. If the order does not change, then no rearrangement. So if it's secondary going to secondary, it's not going to take place. But if it's secondary going to tertiary, it will take place. If you have this, of course, it's going to change to tertiary, but this is not what you started with. You cannot do rearrangement and then another rearrangement. Rearrange of the rearrange doesn't take place. It's just one rearrangement that either takes place or it doesn't take place. It would take place only if the order is going to change. This is the most complex case of the rearrangement that it could take place, so you should at least seen it once, so in case you face it later for the exam, not for the exam, but at least for the homework questions. In this rearrangement going from a secondary to tertiary, this is a specific case. Okay, you can see like increase in the carbon chain or the size of the cyclic system when it's going from a secondary to tertiary. If the cyclic system is attached to carbocation and is substituted, like if this is not going to happen if you didn't have the methyl group here, because it's already secondary. But since you have this methyl group, by joining or increasing the size of the cyclic system, you're going to have a tertiary, and if it's a tertiary, it's going to happen. So this is the specific case that you will see on the homework only. And before going to the other type of reaction, I'm going to answer your questions at this point. Okay, what would be the first step? This is the anti-Markovnikov. Rearrangement would also most likely is going to take place. Yes. What's the first step? H adds to, so are you ignoring the peroxide? What is the presence of, how is the presence of peroxide affect? Peroxides alter the reaction, right? The mechanism of the reaction. You're not going to get H plus attacking the CC double bond. ROOR is called alkyl peroxide. Your alkyl peroxide is a catalyst that changes the mechanism of reaction from carbocation to free radical. What is the first step? First thing that is going to happen here, your ROR is going to break down to RO free radical plus RO free radical. Second, RO free radical is going to react with HBr and it will give you ROH. What's the other piece? Plus the Br free radical. Okay, plus the Br free radical. Now, your electrophile is the free radical of Br, is not the H plus. Okay, so this combination, okay, this combination is going to give you Br free radical, basically. Now, the Br free radical has a choice to attach carbon 1 or carbon 2. Which one is going to happen? Carbon 1 or carbon 2? Okay, you have to see if it attaches to carbon 2, then carbon 1 would be the free radical. If it attaches to carbon 1, then carbon 2 would be free radical. So it will attach to carbon 1. So we will get this as the intermediate that is forming now. So Br attaches to this carbon and this would take the free radical. Okay. If the free radical takes here, then on the next step, okay, on the next step, hydrogen is going to come in and form bond with the CH3, get the CH2, and you get CH2Br. This is an example of anti-Markovnikov. So this product is anti-Markovnikov. Anti-Markovnikov product. And how do we know it's anti-Markovnikov product? Anytime. And these are, when I say anytime, and hint, so write this as a hint to yourself. Anytime you see peroxide in the reaction mixture, or hydrogen peroxide, alkyl peroxide or hydrogen peroxide, any of those two, in addition reaction, your product is going to be anti-Markovnikov. What is anti-Markovnikov? Hydrogen will add to carbon with least number of hydrogen. Br will add to hydrogen with greater number of hydrogens. Okay, so you get the two. You get the anti-Markovnikov addition. Okay, that was for Anti-Markovnikov example. That was one of the questions. Rearrangement, we worry about rearrangement when there is carbocation only. Okay, when there's carbocation, you have the rearrangement, or you don't have rearrangement. But when it's like you don't have carbocation, then don't worry about the rearrangement. The other question that was was emailed to me. How do we know that nucleophilic property is increasing this way? Why this is a better nucleophile than CH3, CH2O, and why CH3, CH2O is a better nucleophile than CH3, 3CO. If you look at the conjugate acid for this, this is coming from conjugate acid. The conjugate acid for this one is CH3, CH2SH. And this one is the CH3, CH2, CH2OH. So which one is a better nucleophile in this case? The size of oxygen compared to sulfur. If this is coming from a stronger acid is a weaker base. This one compared to SH is a stronger acid than the OH. So there are few factors. But what affect the nucleophilic? Remember, when you are comparing I with the Br, which one is the better nucleophile? Can you tell me which one is the better nucleophile? I minus or Br? I is a better nucleophile. And Brianna, this was your question, right? This was your question. So the more, yes, let me see what was the other comment. Weakest base, okay. Weakest base, better nucleophile. So which one is the weaker base? This is coming from a stronger acid, so it's going to be weaker base. Okay, stronger acid, weaker base. What's doing this? So if it's coming from a stronger acid, it's going to be weaker base. It's going to be better nucleophile. It's coming from a stronger acid, weaker base, so it's going to be better nucleophile. The other factor was the polarizability. I minus is better than Br because it's bulkier and it can reach the nucleus better, bigger size for just this element. Okay, so weaker base, better nucleophile for that. What about this case? How could you justify this one? The slide in previous chapter, it says, one of the slides, you need to look for that slide. It says bulkiness of the nucleophile is going to affect the nucleophilic property and is going to make it less strength. That is going to lower the strength of the nucleophile. So this is bulky compared to this one, is going to be less. The nucleophilic effect for this one is going to be less than etoxide. TB-etoxide is more bulky than etoxide, so etoxide is going to be a stronger nucleophile, a better nucleophile. Okay, is 9:48? We don't have lecture tomorrow. I'm not going to post the exam until Sunday. I want you to study, do the OR assignments, do the co-op assignments, work on the assignments. Make sure you turn those assignments in. and you know, maybe like Saturday afternoon, but you have the Sunday. I might do it on Saturday afternoon for people who already have turned in their assignments. If you're done with your assignments, you could do your you could start your test Saturday night as soon as I have it. But I had an email regarding the access code or password for the honor lock. Is an auto-generated access code. So if you do your setup properly, it should not ask you for access code again. And for those of you who took the quiz already with the honor lock, did anyone experience problem? Because that's the most reliable external tool at this point for testing. If anybody had problem